In our last video, we just derived the ligand field splitting diagram, or the ligand field diagram, for an octahedral complex. And we did this by looking at the way in which our ligand orbitals, which we represented as just simple s orbitals, could interact with the 5 different d orbitals on our transition metal complex. This picture here should hopefully be a review. If you're struggling with this, I advise that you go back and rewatch the last video and do some practice problems on deriving the ligand fields from our problem set on Wednesday and Friday for class. What we're going to do is we're going to expand our understanding of the way that ligands can interact with our d orbitals today. Because as we imagine, when we're looking at these, we can think about our ligands as being a lot more complex than just simple s orbitals. As it turns out, this model of using simple s orbitals is modeling what's called a sigma donor-like behavior, meaning we're looking at electron density that is only localized along our bonding axes. So what happens if we start to change up our ligands, if we have anything other than essentially a hydride ligand, something that just has that s orbital? Well, we have to start considering other orbital interactions that can occur. So let's look at something like a chloride complex, right? So we have these metal chloride bonds that we're looking at. Now, the challenge here, the new wrinkle that's brought to foot is that these chlorides are not just s orbitals, right? There's electrons that are sitting in our 2p orbitals as well. Actually, with chlorine, we're up to 3p. But we have electrons that are sitting in these p orbitals as well as our s orbitals. And so we have a lot more combinations that we can consider. We still have essentially that sigma donor-like behavior that we can draw for our EG set of metal orbitals. So again, this is the x squared minus y squared d orbital, as well as the dz squared orbital. And here we've drawn these out and they mirror that sigma donor behavior that we can see just with s orbitals, where we have that electron density that is localized along our bonding axis. So directly along our x, y, and z axes. And we can see that these directly overlap and interact with our d orbitals on our transition metal. But because we have access to these p orbitals, not only do we have this sigma donor-like behavior, but we can actually start to draw pictures that look kind of like pi bonds, right? So this ligand, the chloride ligand, is what we would call a pi donor ligand. Everything is a sigma donor, right? All of our ligands that we are going to look at are sigma donors, but they can also have extra classifications. So in the case of a chloride, we call this a pi donor because I can draw out these p orbitals along my axes, right? And they don't have the electron density localized on our bonding axis, right? It's orthogonal to our bonding axis. And yet we can draw out orbitals and bonds that look an awful lot like pi bonds, right? Now, so far it might not look like a pi bond because we have multiple different atoms and we have our d orbital, but at the very least we can see that here, as drawn, I have dxz, and I can forcibly kind of draw several of these p orbitals to line up with dxz. And so what this means is that that T2G set of orbitals on our transition metal can now actually start to form bonding and antibonding molecular orbitals. So there's a set for DXZ, there's a set for DXY, and there's a set for DYZ. We can draw each of these out along these different orientations, but when we have a pi donor, we now have access to a number of different bonding and antibonding orbitals. So how does this change our picture? How does this change our ligand field? So again, we can start to mix these p orbitals with these central d orbitals for our T2G set. And so what we end up with is actually a more complicated set of our molecular orbitals. In this case, we now have a bonding set of our T2G orbitals that are mixing with these ligand pi orbitals. And if we can generate a bonding set, we have to be able to generate an antibonding set as well. So here we have a higher lying T2G orbital set that's actually antibonding. And what we can see now is that this delta octahedral, the difference in energy between our more localized d orbitals on our metal, has actually gotten quite small because of this interaction with our pi donor. And so we can see that there's a dramatic effect on the molecular orbitals when we have other types of ligand orbitals that can mix. So in this case, we're looking at the addition of these ligand pi orbitals. And so this is our pi donor set, something like chloride, where we have filled orbitals that are our p orbitals along our bonding axes. So this is what we would call a pi donor. Well, like I said, this is describing filled orbitals along our bonding axis. But what if we have open orbitals? So we've looked a lot at metal carbonyl complexes. So this is something that we're exploring quite a bit in the lab portion of this class. But carbonyls are a very well-studied class of ligands, and they bind very tightly to transition metal complexes. So why is that? Well, it's because these are both sigma donors, meaning they have electron density that can be donated directly along our bonding axes, right? This leads to the formation of that Eg and T2G set of orbitals. But now there's actually also a set of interactions that can occur between our empty pi star orbitals for the carbon monoxide, right? So we not only do we have pi orbitals on that CO ligand, but we also have accessible pi star orbitals. So if we're going to draw out what this looks like, it's actually going to look very similar to our sigma or our pi donor case, where we have these pi star orbitals that now we can see or have some arrangement where they line up or match up with the shading of our T2G orbital set. So not only do pi donor ligands interact with our T2G set, pi acceptor ligands actually also interact with our T2G set. So here we're not looking at the filled orbital, we're actually looking at the empty pi star orbital. And when we're talking about this donation, it's actually filled metal orbitals that are donating into this pi star orbital of our ligand as drawn. And so this has some interesting effects, right? We can kind of do some resonance like pictures to think about this, right? This is what we call backbonding. And this is again where our filled metal orbitals are mixing and interacting with our empty ligand antibonding orbitals. So what does this look like if we're thinking about kind of a Lewis structure like picture? Well, this idea of back bonding is where we think about a strengthening of the bond between our metal and our carbon, and a weakening of the bond between the carbon and the oxygen. Hopefully you're having a little bit of like a aha moment here as you're looking at this structure and thinking about our computational reports and our computational studies that we're doing in the lab. There's a reason that every one of our complexes has at least one carbonyl ligand. And there's a reason I was asking you to study and investigate the change in our metal carbon bond length and our carbon oxygen bond length over the course of our optimization cycles. And the reason for that is actually the influence of backbonding. And so this kind of equilibrium arrow is drawn up top. It's actually more of like a resonance picture if we were going to try to use some organic chemistry lingo here. But what we're describing with backbonding is essentially these two different states, right? So we imagine our initial state is being our metal with a filled d orbital, and this other state that we are evaluating is actually an increased bond order between our metal and carbon, and a decreased bond order between our carbon and our oxygen. So if we were going to study this and look at this effect, we might want to use IR spectroscopy, right? Infrared spectroscopy. As I've heard some people call it, coming into 484, right? We can call this carbonyl spectroscopy because that's the main application we've seen up to this point is identifying carbonyls. And so if we're going to look at carbon monoxide, right? C triple bond O, the free CO stretch, right, for a free molecule of carbon monoxide is about 2143 wave numbers. However, a typical carbonyl stretch, a CO double bond, is somewhere around 1600. So we can actually study these metal carbonyl complexes and look for these CO stretches to describe the degree of backbonding. So here we have an isoelectronic series of the vanadium carbonyl, the chromium carbonyl, and the manganese carbonyl. And what we see is that they have different IR stretching frequencies for this CO bond. And at the top, we see that the vanadium complex, right, has the lowest stretching frequency. And that means that that vanadium complex most closely resembles, right, the carbonyl of this set. So we would say that the vanadium complex has a significant amount of backbonding due to this data that we can gather from the infrared spectrum of this vanadium carbonyl complex. At the other end of the spectrum, when we look at this manganese carbonyl complex, it has a stretch that is the closest to the free carbon monoxide, which means that for the best representation for the manganese complex is actually as the C triple bond O, right? So we would say that there's the least amount of back bonding with the manganese. So we can tie this directly to what we could call the electron density of the metal. The greater amount of electron density on our metal, the greater amount of back bonding that can occur. So we see that the vanadium complex has a negative charge. So we would assume that that means that there is a greater amount of electron density on our metal itself that could be shared with the carbonyl. So how does this influence our molecular orbital diagram, right? How does this picture get even more complicated when we start to factor in this idea of a pi acceptor ligand? Well, the answer is it gets a lot more complicated. And the reason for that, again, is that we are now mixing these empty ligand pi star orbitals with our d orbitals. And so again, if we have this mixing, we can generate both an antibonding and bonding configuration. And what we see here is that the value or the degree for delta octahedral, right, that delta E term, increases pretty dramatically for pi acceptor type ligands. Because now we actually have empty, low-lying T2G orbitals that arise from the mixing of this pi star orbitals with our d orbital set. And so if we're going to break this down, we can actually say that the type of ligand, whether it's a sigma donor, pi donor, or pi acceptor, has a direct impact on delta octahedral. And so we would see that the pi donors in general have the smallest value of delta octahedral. And again, this is the delta or the difference in energy between our d orbitals as they are more localized on the metal center. Our sigma donors, or what we would say pure sigma donors, because everything has some sigma donor character, is in the middle here, right? It has a middling range for delta octahedral. And our pi acceptor ligands actually have the greatest value of delta octahedral. And the reason for this comes from the actual nature of our T2G set. For our sigma donors, what we derived in our last class is that sigma donors, these T2G sets of orbitals, are essentially non-bonding, right? They have an orbital coefficient of approaching 1 for our d orbitals because there's nothing for them to mix with when it comes to our ligands. So these are essentially non-bonding orbitals. However, when we look at the pi donor case, this T2G set for pi donors is actually antibonding, right? This is what arises from the mixing with a filled set of p orbitals on our ligands. And lastly, if we looked at pi acceptors, right, this T2G set for a pi acceptor ligand type is actually the bonding set of orbitals, right? And it's the bonding set of orbitals because they are mixing with the empty pi orbitals on our ligand set. And so we can roughly say that in general, pi donors would have the smallest delta octahedral, sigma donors would have a larger delta octahedral, and pi acceptors would have the largest value of delta octahedral. And this leads to what we call our spectrochemical series. And so we have our range from smallest to largest delta octahedral, and we can actually arrange ligands based on whether they are pi or sigma donors or pi acceptors on this spectrum. And so on the far left of this spectrum, we have things like our halogens. In this case, right, we have chlorine or chloride listed here. This is the example we used as a typical pi donor, because these have electrons that are lying in p orbitals that can interact with our metal orbitals. In the middle of our series here, we have things that are more strictly pi or sigma donors. Something like ammonia or hydride would fit in as our pi donor set, because these only have electron density pointed along our bonding axis without significant amounts of p-like character that can interact with our metal orbitals. On the right-hand side of our spectrochemical series, we have our largest value for delta octahedral. And these are again our pi acceptors. So things like NO2 or CN minus or the carbonyl, right? Carbon monoxide or NO plus, right? These are compounds that have a low enough lying set of these pi star orbitals that they can mix with our transition metal complex. And so your first instinct might be to memorize this series of our ligands for our spectrochemical series. And while that's not necessarily a bad idea, what's much more important to recognize is the ordering that occurs. If we have a pi donor, it will have a smaller delta octahedral. If we have something that is more along the lines of a pure sigma donor, again, that's pretty much going to be ammonia or hydride in terms of what we're looking at. That's going to be more in the middle of our value for delta octahedral. And if we have something that's a pi acceptor, so on the far right-hand side of the spectrum, it's going to have our largest value of delta octahedral. It's much more important that you can identify or at least rationalize why something is a pi donor, a sigma donor, or even a pi acceptor than it is to memorize this series of ligands. And what we're going to be looking at from here on is actually how these ligand types or changing the ligand types influences our other ligand fields. So if we look at something that is square planar, and now we move away from just these spherical s orbitals, and we begin to evaluate our potential for p orbitals along these axes, how might this change our ligand field that we could derive? We could also look at this for a linear compound, right? How does the inclusion of p orbitals change the way that we can derive a ligand field? This is what we're going to be looking at in class as we start to generate more advanced and complicated ligand fields by incorporating our understanding of the shape of p orbitals and combining this with our initial understanding of these sigma-like orbitals that we created in our last class, right, last week. So we're going to continue to expand our understanding of metal ligand bonding by looking at these other types of ligands as they interact within these geometric patterns with our metal centers.